Good afternoon, everybody. Welcome to Back to Basics. Sorry for the blip in uploads. My schedule has been completely messed up, but we'll get back on track here. Anyway, this week we're going to talk about diodes. Very briefly, we're not going to go into the large number of various different types. We're just going to talk about your generic bog standard diode, like this 1N4007 right here. Last week we talked about semiconductor doping and the methods by which we add impurities to silicon to create N-type and P-type semiconductor material. A link right there. This week we're going to talk about how a diode works and why those P and N-type materials are important. Now, inside of a diode, you'll have the leads coming in, and then you'll have a ceramic encapsulation, and then another lead. Now, inside of this diode is a much smaller area. Another lead comes in, then you'll have the little metal cap, and then inside that will be a chunk of silicon, and then you'll have another metal cap, and then that goes out. Now, I've actually seen diodes where they failed rather spectacularly and cracked right in half, and you could actually see this piece of the diode, and it's surprisingly small, even for a power diode like the 1N4007 that has a voltage rating of 1000 volts, and that's the reverse voltage rating, and we'll talk about that in just a minute. Pardon the cats, they were just sharpening their claws. Now, what's happening inside this little silicon wafer? Well, in that silicon wafer, we are going to have a section of P-type semiconductor material. And this is actually typically done with just one crystal. They don't take two pieces of silicon and squish them together. They typically just dope the silicon and leave it all as one crystal. Now I need my eraser. I'll just use my finger. Okay. So you have a piece of P-type silicon and a piece of N-type silicon. I guess sometimes they are mated together, but in most cases it's just one crystal, and they dope the ends of it. So what happens when you join these together is actually kind of interesting. Now, on the N-type side, you have a bunch of free electrons. Remember, because this is done with pentavalent doping material, so it has an extra electron that floats around in this material. And the P-type semiconductor has what we refer to in the electronics industry as a bunch of holes, because it's lacking electrons. So we'll just draw in real quick a bunch of little holes. Bear with me. I probably should have sketched this out before I started, but that's all right. There we go. Anyway, so in the center here, we get an action where, hey, Jack, cool it. One of my cats is spazzing out. Anyway, so we get this region in the middle here, and it's very, very small, where electrons flow into holes in the N-type, and a equilibrium is reached just in one little section of the material here. So the properties of this area are very interesting. For all intents and purposes, it acts as a conductor, or sorry, not a conductor, an insulator, because it sort of resists the flow of electricity. Now, in this direction, it doesn't act against the flow of electric current. Let me draw out the actual symbol for a diode here. So in regards to the P and N type material, this is where the diode. Now remember, oops, that's way off shot. Let's scoot that up. All right, so remember with conventional electron flow, or not conventional, with electron current flow, the electrons actually flow backwards to the way we're used to them flowing. And that's actually really important when we're talking about diodes. And I keep doing stuff out of shot, so we'll scoot that up even further. So electron current flow is important when we're talking about diodes because it's a lot easier to visualize the way they work. With conventional current flow, of course, we normally think that it goes in that direction. But with electron current flow, it's going from negative to positive, and this is why, and we'll talk about why this is important for diodes now. So if you try to get electrons to flow in this direction, nothing's going to happen because these holes will fill up and then there's nowhere for those electrons to go in this depletion layer. So it completely resists flow of current going in that direction. But if we have electrons flowing in this direction, these electrons get kicked out and they fall over into these holes, and then these holes fill up and then they get kicked out and you get current flow. Now it takes a little bit of energy to break down that PN junction, and with silicon diodes this is typically well, the textbooks say 0.7 volts, but anymore these days, because they've gotten really good at manufacturing these, the voltage is actually much closer to 0.5 volts. And with germanium diodes, the forward voltage is 0.3 volts. And that's the amount of energy that it takes to overcome that little speed bump here when flowing in the correct direction, and then current flows. Going in this direction, however, it takes a whole heck of a lot more voltage to start forcing stuff through. And in the case of a 1N4007 diode, that voltage rating is 1000 volts. It's not typically a good idea to reverse bias a diode, except in the case of Zener diodes. But we'll talk about Zener diodes in more detail in another video, because I need to research the science behind them, and they'll take an entire video all on themselves. So anyway, there's an easier way to visualize what's going on here. Now I really do need my eraser. There it is. And we're actually going to visit the water analogies that I previously visited when talking about amps and volts and various different current type stuff. I'll bring that back into shot. So let's imagine that we have yeah, we'll call this and then we'll do this, and this is a dam, and on one side of the dam is full of water, and this is our electrons. This is our N-type semiconductor material over here. And then this is our P-type semiconductor material, which basically has no electrons in it at all, no extra electrons. So when you forward bias this diode, it's very easy to get electrons to spill over that edge. You just add a little bit extra and they start spilling over the edge, and then current starts to flow. But in the opposite direction, you have this big potential difference here that you have to overcome in order to get current flow in the opposite direction. Now, interestingly enough, with a P-type, or a 1N4007, this potential difference is basically 1000 volts. That's what it takes to go in that direction. But the potential difference to create current flow in this direction is only this much, which is about 0.5 to 0.7 volts. And that's how diodes work. There's a whole lot more quantum science and tunneling and much more complicated stuff that we could talk about, but we're just covering the basics here. So, just in review, we have the PN junction here, which is a sort of neutral insulating layer that is formed by an equilibrium being reached between N-type semiconductor material, out of shot again there, and P-type semiconductor material. And this junction is what keeps current from flowing backwards through the diode. But forwards, it's very easy to bump that voltage over and then create current flow. So anyway, start a discussion in the comments below if you have any questions. If you enjoyed watching, go ahead and click that like button. If you haven't already, consider clicking about here for a subscribe button. Right over here will be a video that YouTube thinks you'll like based on your watching habits. Right here will be the Back to Basics playlist, and right here will be the Patreon link by which you can support further videos like this one. Patreon supporters do get to watch these videos 1 week in advance of YouTube subscribers, so that's just a little bonus if you pledge like $1 a month to help me out here. So thanks so much for watching, and we'll see you next week. Bye-bye.